Does everyone see a new screen?
Yeah.
Okay. All right, so let's just do substitution review. Okay. So, okay, so for both of these types of reactions, we are going to have some type of the basic reaction is alkyl halide reacting with some nucleophile in some solvent, and then we're going to have our substitution product. And there's basically two mechanisms. SN2, SN1. So, oh yeah, substitution product plus, I'll put over here a leaving group. There's two mechanisms. Let's draw a example here. Chlorine. And we'll use azide as our nucleophile here. So this is negative, that's negative, that's plus. Question, okay. Would azide, N3 minus is azide. Would this be a good nucleophile or a bad nucleophile? It's a good nucleophile. And what are two reasons why azide would be a good nucleophile? You've got a negative charge on nitrogen, right? So that's good. What's the other? And in fact, both ends have got negative charges on them. So both nitrogens have a negative charge. So that's, and it's linear, right? So there's the two reasons is that it's got negative charge and it's linear. So the two mechanisms, SN2. So this one is the one where the electrons attack the partial positive and you get, and the leaving group leaves. So the rate for this reaction is some rate constant, and it's dependent upon our Cl and azide. Because in the energy diagram, the rate determining step, it involves both. So this would be free energy, and this would be the reaction coordinate. It would just be a single sort of, one hump in the middle. And the transition state here would be, it would look like a, in this case here, we'll draw it like this, R. The leaving group is leaving, and the nucleophile is attacking. And so this would be a trigonal bipyramidal sort of structure, and it's transient species, and then before you know it, you're going to have your product. So the nucleophile has to attack from the opposite side. So if you've got a secondary alkyl halide, like say this one, actually let's just do OMS. So this would be the mesylate, which is a good leaving group. If we had a nucleophile like the cyanide nucleophile, and it attacked, comes in from the opposite side. This is going to leave. We are going to get, our product will be inverted because the nucleophile has to attack from the opposite side. So if we were drawing, so it would have a very similar structure to what we've drawn over here, except for, let me see if I can draw this with the proper stereochemistry. I think this would be the correct one. It's going to be hard. I might have drawn it with the wrong stereochemistry here, but anyway. The key point, though, is that it goes through whatever you had. If it was going forward, it would end up being backward. And if it was backward, it would end up being forward. The key point is that there's inversion. Inversion of stereochemistry. Okay, so that's basically the SN2 mechanism. Now with the SN1, the difference is, we'll draw primary, tertiary. For an SN1 mechanism, the first step is that the leaving group departs and you form a carbocation. And then in the second step, stop that, the nucleophile, whatever it would be, would come in and attack. And it can attack from either side. So we are going to end up with two potential products here, and they're going to be 50-50. So we could have the nucleophile forward and the ethyl back, or the ethyl forward and the nucleophile back. And so this will be 50% this and 50% this. And so the best way to draw this, because that's a lot of drawing, is to just draw a squiggly line for the nucleophile. Okay, yes, we will go over, okay, yes, we will go over that in a second. So there's a question about, can you go over why a linear molecule makes a good nucleophile? We're going to go over that in a second. So the consequence of an SN1 reaction is that, so for SN2 we get inversion of stereochemistry. For SN1 we get racemization. So we basically destroy it, right? We start with pure one stereoisomer and then we make 50-50% mixture of the other two. So it's, in my personal opinion, it's not a good thing, but that's just one of those things, right? There's a question about why wouldn't the ethyl group be a squiggly line as well? Yes, some people draw the ethyl group as a squiggly line as well. I'm just basically saving time with that. So, because it would be, yes, technically you could draw it like this. But drawing one like this basically means that all of them could be, you could have another squiggly line for all of those. So there is no stereochemistry, I guess. So it's not necessary to do that. Now, the energy diagram of an SN1 reaction is slightly different. So because we make this intermediate, there's another point on the diagram. In the SN2 reaction, I don't have a laser here, but over here, we don't actually have, and there's no intermediate. There's just a transition state. So, and remember, you can't isolate transition state. So when it comes to an SN1 reaction, we have our starting material. We need to form our carbocation, which is up here. So up. And then say our product's down here. Then there's another hump to get to your final product. So this would be your product, and this would be the carbocation. So when we were doing our, so what is going on? Okay, so we have our what is going on. The first, what's going on, like SN1 versus SN2. There was basically, we had 3 different choices, CX, the first question is the type of alkyl halide. Is it primary, secondary, or tertiary? Because primary alkyl halides can only do SN2. Tertiary can only do SN1. And why can tertiary only do SN1 and primaries don't? This all comes down to the carbocation stability, right? So when it comes to carbocations, the most stable was was tertiary is more stable than secondary, which is more stable than primary. So this is the most stable. So that is why tertiary alkyl halides can undergo SN1 reactions. Primaries don't, because the intermediate is not stable. So if the intermediate's not stable, that means that if we had a primary carbocation, this energy diagram would be way up here. So it's too much energy to get there. And the reason why SN2 reactions, primary are only, you can't have SN2 on a tertiary, comes back to this attack of the nucleophile. If you've got large groups, say a methyl, I'm drawing on all the protons for a reason. If you're the nucleophile, you need to attack from the opposite side. And when you have all of these large groups here, it basically blocks this attack. So with tertiary, this attack is impossible. Tertiary, the attack is impossible. And then with secondary, you had a choice, right? And so it could be either. And so as we just did with these last questions, the 2 important things were the nucleophile and the solvent. Good nucleophiles favor SN2. poor nucleophiles favor SN1. Aprotic polar favor SN2. Protic, these would be polar, favor SN1. So a nucleophile, good nucleophiles favor SN2. The reason is right up here in the rate equation. The nucleophile is in the rate. The rate determining step of a SN1, the rate equals some rate constant times Rx. There's no nucleophile there. So if you want to favor one over the other, you would use a good nucleophile for an SN2, you'd use a poor nucleophile for SN1. Protic solvents, they do two things. They can stabilize the carbocation transition states. So that's going to favor SN1. And polar protic solvents also solvate nucleophiles. So this is going to reduce the rate of an SN2 reaction, right? So if the nucleophile is solvated, it can't undergo that, it can't attack, right? So if it solvates a nucleophile, this is going to reduce the rate of a SN2. Stabilizing the carbo transition state, this is going to increase the rate of an SN1. So it's going to favor SN1 and it's going to reduce the rate of SN2. So those are the, so when you've got a choice between either, look to the solvent and look to the nucleophile. That was, someone asked about nucleophiles. So remember when we're talking about nucleophiles, what makes a good nucleophile? Basically, what we did at the start of term with regard to bases, whatever was a strong base was a good nucleophile. So basis like nucleophilicity, basically that parallels basicity, if we're going to use that. Except for a couple of examples. And the examples were polarizable, I guess, polarizable. Polarizable anions were good nucleophiles. But they are terrible bases. And so these are species that are low on the periodic table, which stabilize that negative charge in the large orbital. Things like iodide, sorry. So sulfur, anything which is when you're getting lower on the periodic table, bromide, these would all be decent nucleophiles, but they are terrible bases. We'll talk about the leaving groups in a second. So these are good nucleophiles, but terrible bases. So that's one area where nucleophilicity doesn't parallel basicity. The other one was that if you've got molecules that are, or anions that are attached to which have bulky substituents on them, like tert butoxide or say tert butyl lithium. These are very bulky molecules and they make terrible nucleophiles because the negative charge needs to attack a nucleus, and because they've got all this stuff Okay, just think of if you are walking in a door and you're walking in the door by yourself. Easy to do, right? Open up the door, walk in. Now, pretend you're walking in the door and you're carrying 10 bags of groceries. You are banging into the walls. The area which you occupy is now a lot larger, and you've got to like turn your body to get it. Well, at least I do, to get in the door, and so you're just taking up more space. So any molecule which is super bulky and takes up space, these reduce the nucleophilicity of the molecule. But conversely, if you are a linear molecule like these guys here, which I'm drawing, these are wonderful nucleophiles because they don't take up any space because they're linear. So just as bulky things would make something a bad nucleophile, a linear molecule makes something a better nucleophile. So I hope that answers the question about why something which is linear, this is good. Whereas something which is bulky, this is bad. For nucleophilicity, we're not talking about, like later on, we're going to talk about bases. That's slightly different. Now, there was another question about leaving groups. So leaving groups are part of each rate determining step. So for the SN1, the leaving group has to leave, right? The RX. And for an SN2, the RCl here. So leaving groups are important for both reactions. The difference is some leaving groups are good leaving groups and some leaving groups are bad leaving groups. So when we talk about leaving groups, like for example, let's pretend that this is this is our question. So we're going to do a substitution reaction here. We've got our nucleophile. And we've got our alkyl halide over here. And I've got drawn two species, like two, functional groups here. We've got this and this. And my question is, if this nucleophile was to attack, would it attack, and both of these carbons have got delta positives on them, right? We got polar bond to delta plus, delta plus. Is the cyanide going to attack here, A, or is the cyanide going to attack here, B? Because they're both primary, this is going to be SN2 reaction. There's no choice in the matter. But which route is it going to go? Is it going to go down route A or route B? The answer is yes, you're right. It's A, because bromide is a far better leaving group than hydroxide, right? So this is a great leaving group, and this one's a bad leaving group. Why? So remember, good leaving groups are weak conjugate bases. Or the conjugate base of a strong acid. So they're anions which can stabilize a negative charge really well. Bromide can stabilize this negative charge in its big orbital. Hydroxide would only be stabilizing it because it's electronegative. But this is a strong base, right? This is a strong base. So strong bases aren't good leaving groups. You want a exceedingly weak base. So that's how leaving groups come into play. Like this would be a good type of question to ask on a test. Like, what's the product of this reaction? And you could have cyanide substituted there on the OH or on the bromide. And it's mainly a question about what's a better leaving group. Said another way, that's what that's about. Oh boy. Okay, so that was that. Today's Thursday, isn't it? Okay, that took way longer than I was hoping. Okay, so we still have to do one last thing. And I don't know how in the world we're going to do it in one class. There is the sister part, and this will be the preview for next class, I guess. There's the sister equation or the sister reaction for what we just did. So substitution reactions, there is the thing which goes along with this is elimination reactions. And so with elimination reactions, let's just draw this here for a second. Oh no, let's do this. Okay, we'll draw an extra carbon here. So an elimination reaction is the following. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So in an elimination reaction, we actually make an alkene. And the base, instead of attacking the carbon, grabs a proton from carbon 4 to make an alkene. So this is where your base gets protonated. So you go from being a base to the conjugate acid, and you still have a leaving group which leaves. And so the only difference between this reaction and the substitution reaction is that bases remove protons, or a proton, I guess. Whereas the nucleophile, if it was a substitution reaction, attacks the carbon. And so remember, bases and nucleophiles are very similar, right? They're both Lewis bases. They both got lone pairs that they can use. But the main difference is that bases will remove protons, whereas nucleophiles will attack carbon. So we've got, our starting material is an alkyl halide. We've got our Lewis base. In this case, it's going to be a Bronsted base as well. And we've got our solvent. So it's the same three components to a substitution reaction, except for these undergo elimination reactions. And so there's two types of, I got like 1 minute left. There's basically two types of elimination reactions. One is called an E2, and one is called an E1. So it's just the same, it's very similar to SN2 and SN1. E1 eliminations involve carbocations. E2 have got a transition, there's no intermediate. And they've got a stereochemical requirement. And they have a stereo. So just like in SN2 reaction, the nucleophile had to attack from the opposite side of the leaving group. In an E2 elimination, the proton has to be a specific way. So yeah, this is what I guess what we'll have to do a little bit of this on next Tuesday, I guess. So we'll basically cover the basics of an E2 versus an E1. And yeah, I guess that's what we'll do that on Tuesday. This so yeah, today's class went way slower than that. I was kind of hoping to actually, well, we did a nice little review of the SN1 and SN2, so that's good. This doesn't leave us much time for this, but that's that, I suppose. But okay, so yeah, that's what we'll do on Tuesday. We'll do a quick little thing on E1 and E2. The nice thing about these is that there are certain conditions of a reaction that greatly favor elimination reactions over substitution reactions, and hopefully that will be readily recognizable. And so, yeah, that's what we'll do on Tuesday. I'm gonna the very last assignment I'm gonna post on Sunday. And that's basically going to cover stuff from the energy diagrams and the substitution stuff. And it'll be a good practice for these types of questions for the final. So that will come out on, everything goes according to plan on Sunday. And it'll be basically due right at the very end, like when the final exams are. So it'll be a good practice. In fact, yeah, so. Any questions before we end class? Okay, well, if not, then I'll see everybody on Tuesday.
Thank you.
You bet.